prime numbers are natural numbers that are greater than 1 and whose only factors are 1 and itself. So the first prime number, so all the prime numbers less than 100 is 2, because 2 can only be divided by 2 and 1. Same for 3, 5, 7, 11, 13, and so forth, while, for example, 10 would be a natural number greater than 1, but 10 can be divided by 2 and 5 as well, so 10 is not a prime number. And we have this list of all the prime numbers less than 100 here. And prime numbers are very important in computer science and mathematics. For example, we may need prime numbers for certain algorithms in cryptography. We may need prime numbers for certain random number generators. Error correcting codes may require prime numbers, or calculating hashes. Hashes is something we did a few weeks ago when we started with hash tables. So we actually need prime numbers for lots of examples or for a lot of algorithms in computer science and mathematics. So what we want to do is we actually want to generate prime numbers efficiently. And we will study today a few algorithms that allow us to generate prime numbers. Has any of you ever looked into generating prime numbers? If you have, maybe send me a signal, positive or negative if you have not. Because we have this list here, and actually we want to see how we can generate more prime numbers. One person has done this. Maybe you want to tell us either orally or in the chat how you have generated prime numbers and what you needed them for. And feel free to answer either orally or in the chat. I came across this topic in also my first year when I studied computer science in my bachelor's. I actually sat in the university library and there was a book, an entire book about prime numbers and how to generate them, which I found very interesting, and I read that book. Today, we're obviously just looking at some strategies, but we could probably spend the whole term just on prime numbers if we wish. But I'm just trying to provide you with the essence. So one student needed this for 2 to the x minus 1, okay, for that problem. So now let's think about how we can generate prime numbers. And I'll implement a couple of algorithms today, and we will start with one and we will wonder if it's efficient or not, and then we will try to look at different strategies. So we can say get primes in interval naive. So what I want is I want to get the prime numbers in the interval from 2 to n, where n is not included. So n is sort of the upper bound of the interval, which is excluded. So if n was 100, we would want the prime numbers from 2 to 99, where 99 is included. So what we can try is we can try something like this. We can say we go through the range from 2 to n, so n is excluded, and we can check if that one is a prime number with a very naive approach, and if so, we yield it. So what I have here is a generator that will successively generate my prime numbers. What I need is this helper method or helper function is prime naive, and we can try to implement this one now. So for a number n, an integer we assume, or a natural number actually, we want to check if this is a prime number. And what we can try is a range, something, we look into the range from 2 to n, and we'll wonder if n can be divided by that index I where we start from 2 and go up to n, where n is excluded. And if we can actually divide our candidate by I, and we use this modulo operator, and if we divide n by I with a modulo operator, and the result is 0, that means that n could be divided by I. And if that is the case, then, well, then n cannot be a prime number. Because, say, if we put in 4 and 4 could be divided by 2, then 4 modulo 2 would be 0 because there's no remainder, because the modulo always gives us the remainder. Then 4 is not possible to be a prime number, and that's why I'm returning false. However, if I can run through the loop and I don't run into the false or return false, then I'm returning true because n could not be divided by any of the integers from 2 up to n minus 1, which is the last one we look at that range. So this is our helper function, and we use this in here, and we can just test it. We can say, I want an iterator here, so get primes in interval naive, something like this, and then I'm starting with a 2, a 3, a 5, a 7, and so forth. What do you think is the complexity of my approach here to calculate or to generate these prime numbers? So you look at this function and you pay attention to this helper function that is called. What do you think is the complexity of my algorithm? O of what? If you have a suggestion, send it to the chat. Got one answer. Let's collect a few more. And it's O of n squared. It's correct because here I have a loop, and in the helper function, I have another loop. So it's O of n squared. It's not very efficient. What we can try is something like this. So I'm calling my get primes interval naive, say on a number like 10,000. And this will be a generator. And if I want to exhaust the generator, or the iterator on that generator and generate all the numbers, what I can just do is I can pass such an iterator to a list, or to the list constructor, and it will eventually exhaust the iterator and then return me a list with all these prime numbers. And I can time this. So for n is 10,000, we will time it. Actually, just will take a few hundred milliseconds, but the time it is running this multiple times. So this takes like 106 milliseconds. If you look into the slides, a few slides away, when I created these slides a few years ago, it was like 350 milliseconds, the number in there, but this was my old computer, and this is the computer I got last year. But we see the exact numbers don't matter anyway, but later we just want to see a comparison of how long this actually takes. So we see it takes 106 milliseconds in average to run our get primes in interval naive for n equals 10,000. And we saw it's O of n squared. So let's think about if we can actually do this faster. And for that, I have a slide. So let's maybe think about some trivial suggestion of how we can improve the algorithm. What we can say is, in our is prime naive, which was this helper function, we traversed from 2 up to n. But actually, we can speed this up, and we only need to go in the helper function to the square root of n, because there's an example here. So for example, we see 12 can be the product of 2 times 6. 12 can also be the product of 3 and 4. 12 is the product of square root 12 times the square root of 12, or 12 is 4 times 3, so 3 times 4 as well as 4 times 3, and 2 times 6 as well as 6 times 2. So we see there is this symmetry. And actually, we only need to run this up to here, and we don't need to do these remaining two ones. So in fact, we only need to run up to the square root of n, because if we run in the helper function up to n, we're just doing a lot of duplicate work because of this symmetry, which is also explained here in the slides with a few sentences, but eventually that's what I've just said. So we can try to implement this and speed it up, in fact. So let's give a shot at this. What we need is essentially just the same outer function as before, which we call get primes in interval naive. And now let's maybe just call it get primes in interval faster. And the function itself will not really change, but it will just call a different helper. And our helper this time is prime faster n. And remember what we did here was we went through from 2 up to n minus 1 included, but we had this symmetry as we saw. So actually we only want to run to the square root of n. And if you try now to implement it this way, and you would say my I runs in a range from 2 to the square root of n, that doesn't work because the square root of n may not be an integer or a natural number, but a float value, then this one here will not work. So I need to write this in a slightly different way. And for this, we will simply use a while loop. So what I can say is I'm starting with I, it's 2. And I could say yi is like less than less than or equal to the square root of n. I would need to import a helper for the square root from the math package, and then I have to round it up. So I have to seal it. Makes the code a little bit ugly, but imagine if I have the inequality like this, while I is less than or equal to the square root of n, I could just square both sides of the, yeah, I can just square both sides of the inequality. So it would be something like I squared times the square root of n squared. And then I can do this with any inequality, but the square root of n times the square root of n is just n. So squaring it this way just looks nicer than putting a square root here and an I there, because then I have to seal it and so forth, which isn't fun. So this one here actually looks much more intuitive. And now I'm checking if n can be divided by I. So if n modulo I is 0, and if so, I'm returning false, then I'm incrementing 1. And if the loop runs through, then I'm actually returning true, because then n is a prime number. So it's more or less just the same approach as in the naive one, but because of that symmetry, we only run to the square root of n. So not very, in terms of coding, not very different. And this is something we can also test. So we said this is the faster one, and we will see 2, 3, 5, 7, and so forth. Now let's test it. So when we ran the naive one for n equals 10,000, we saw it took 106 milliseconds. Now, do you have any guesses how long this may run for the faster one? We will think about the complexity soon, but do you have any guesses, say, how long this would run now with the faster one? where we only run here to the square root of n. If you have any guesses of how many milliseconds this may take, send it to the chat, because all we have done is we have optimized the prime checking. We have not touched this one here, which is calling a different helper. So any guesses what you think before it took 100 milliseconds? Now let us know what you think, how long this would run in with the faster one. One student guesses 50 milliseconds. Any other guesses? I think it will run much faster than 50 milliseconds, substantially faster. Let's run it and let's see. So in fact, it took like 3.2 milliseconds. So a massive improvement to the 100 we saw before, because it comes with a better complexity. What do you think is the complexity of my new approach here? So what's the complexity of this function? We still have a loop. That one doesn't change, but the one we are calling has changed. So what do you think is the complexity of my new algorithm? Since I don't see an answer yet, what do you think is the complexity of the helper, the is prime faster? Because I have a loop, but the loop doesn't run to n, it runs to the square root of n. So what could be the complexity of my is prime faster? That's correct. The helper one has a complexity of O of square root of n. And because that one is called n many times, the main function here has a complexity of O of n times square root of n. And I also have a slide coming for that, because the outer loop runs n many times, but the loop in the helper function only runs the square root of n. So the complexity of this algorithm is O of n times the square root of n. So we got the right answer in the chat, just with powers, that this one here would be the O of n, and or n, and n, the square root of n is n to the power of a half. So this would be O of n to the power of 3 divided by 2, or we just write it out as n times the square root of n. Now it turns out we've already improved quite a lot, because we went down from 100 milliseconds to like 3 milliseconds, which is enormous. But it turns out we can run this even much faster with a few new suggestions. What we need is a new approach. We can further improve this algorithm by thinking about the following. Our new approach will say we are starting from 2, and we know that 2 is a prime number. So all the multiples of 2 are not prime numbers. If 2 is a prime number, 4, which is a multiple of 2, cannot be a prime number, because it can be divided by 2. So all the multiples of 2, once we know that 2 is a prime number, all the multiples of 2 need to be eliminated. The same for 3, because after we have done this for the 2, that all the multiples of 2 have been eliminated, the next number that we're looking at is a 3. And the 3 is also a prime number, because it's not a multiple of 2, so it was not eliminated. So all the multiples of 3 will be eliminated, and so forth. And with this approach, we will try to implement it. We will see that it may run already faster. So what I'm implementing now is, I call this get primes in interval new. And this time we just built one function And what I'm doing is now I'm building a helper list. And the helper list, well, here my code completion already suggests this because I've implemented it before. What I have in here is I'm building a list. And the list will have entries for the 0, which cannot be a prime number. The 1 cannot be a prime number, but the 2 would be a prime number. So we initially say we are building a list which has 2 entries false for 0 and 1. They are not prime numbers. And then I'm adding n minus 2 many true entries. So initially I'm assuming that a number 2, 3, 4, and so forth up to n are all prime numbers. And what I'm concatenating here is I'm concatenating this list with 2 false entries, and I have a list with 1 true entry, and I multiply this with n minus 2, meaning that I'm just creating a list with n minus 2 true entries, and I'm concatenating it with that list. And I'm assuming initially all these numbers starting 2 are prime numbers, but now I'm trying to eliminate the ones which are always the multiples. So I can say I can go through my range from 2 to n, and if my index I leads to a true entry in is prime, then I have a prime number. So when this starts running the first time, I have a 2, and I will be 2. So I'm looking into the first entry of after the 2 falses, and that is true. It's a 2. So I have my prime number. So I'm yielding it. When this generator gets invoked for the next item, I need to remove all the multiples of I. So I have a new loop where I say I'm going through from 2 times I to n with step size I. What that means is I'm looking at I times 2, which would be in the first case a 4, and I want this to run up to n. And with a regular range, I have a beginning and the upper end, which is excluded of the interval. And this is always step size 1. But the range in Python has one more parameter, and that's the step size, which is by default 1, but I can also set it to I, which would be initially here 2. So I'm starting at 2 times I, and then I'm adding 2 on top, and I keep doing this until I reach n. And these ones where J is pointing to cannot be prime numbers because they are the multiple of a prime number. So I'm setting all of them to false. Then when the inner loop has finished, my outer loop will go to 3, which is a prime number. I'm yielding it. Then all the multiples of 3 will be eliminated. Then I'm going to 4, but 4 is not a prime number, so this is just skipped. And I'm going to the 5, and I keep doing this. This approach here also works. So I say this is the new approach, and it's 2, 3, 5, 7, and so forth. Let's see how fast this one runs. So we saw the naive one took 100 milliseconds. The faster one took 3.2 milliseconds. Any guesses that you have how long may it take to run this with my new approach? If you have any, and there's nothing wrong if you guess a wrong number. I just want to see your intuition, what you think, how long this would take. So any guesses that you have, send them to the chat. And maybe some more guesses than before. And then I'm waiting for some guesses here in the chat, how long this would take if I run this for n equals 10,000. But no one here is so one student says some nanosecond number, like 100 nanoseconds. It's probably more than nanoseconds, but definitely in the microseconds. But let's see, let's run it. but I think it will already lead to quite some. Well, it's 499 microseconds, so not nanoseconds, but still already just for n equals 10,000, it's 6 times faster than our faster one. So, because the faster one, the second approach was 3.2 milliseconds, and now we're actually at 0.5 milliseconds. So, quite some speed up. And if you make n larger, you will see the difference even more. We're not looking at the complexity of this one here, but we will slightly improve what we have just done. And when we improve this, then we actually come to our algorithm that will lead to a further speed up. We can wonder if we can further improve this. And in fact, we can improve it because what we have just not done anymore is taking into account the symmetry of these factors. Because our outer loop still runs from 2 to n. And before we've seen when we went from the naive one to the improved one, we took advantage of that symmetry of the factors. So maybe we only need to look at 2 to the square root of n. And in the inner loop, we can make another improvement. So the inner loop right now was that we look at these multiples of I, and we say 2 times I plus I and so forth. But it turns out that we can optimize this further. For example, when we have an example like where we say n is 25 and I is 4, the algorithm will mark numbers which are the multiples of 4, like 4 times 2, 4 times 3, and so forth. But these ones will already have been marked, for example, by 2 times 4 and 3 times 4. So there's already some duplicate work that we are doing. Because this 2 times 4 and 3 times 4, the I was 2 and 3. We can slightly optimize this further, that the variable j in the inner loop traverses or starts at the square of I, so I squared, rather than 2 times I. So this will give us a further speed up of the inner loop. So we can optimize both the outer loop as well as the inner loop. And this is what we will implement now. So I want to get the primes in interval, and this is a so-called prime number sieve. It's the sieve of the Eratosthenes. I'm not sure if I'm pronouncing the name correctly, but that was a Greek researcher who already discovered this method long before our modern times, so probably thousands of years ago. And the beginning is pretty much the same. And I'm just implementing the 2 improvements I have suggested. The outer loop needs to run from I up to the square root of n, and the inner loop doesn't start at 2 times I, but rather I squared. So we've done this trick before, that we said we want to run our I or our I up to the square root of n. It looks better just to square both sides of the inequality. So we say while I squared is less than n, looks better than while I is less than or equal to the square root of n. And if I is a prime number, then I have to eliminate all the multiples of I, but rather than saying 2 times I, we are starting at I squared. And then I'm setting the list at index j to false. And if I've done this, I am incrementing I. And the way this is implemented now, it only has one small problem, which doesn't look that nice, is that I'm first running all of this, and then at the end, the the generator will come into play. It's not really the idea of how the generator works, but the way we're implementing this. This time, we have to do all this preliminary work and eliminate them before we can actually start generating the elements. So this is the upfront work, and then I'm just reading out the actual primes. So this is the only slight disadvantage of this one here, but it doesn't matter for this course. And we can test it. So we are creating a new generator on the interval Sieve. We're getting the 2, 3, the 5, the 7, 11, and so forth. And you saw our third approach from before for the first 10,000 took 499 microseconds, and the sieve will run still faster than this. Let's see how long it will take exactly. But the sieve, yeah, still leads to some speed up, which is like 365 microseconds. And if you make these ends bigger, for example, we can take the approach, the third approach from before, and increase n to 100,000. We'll see the difference becomes probably even bigger. So this one for the third approach, the one just before, for n 100,000 takes 5.29 milliseconds, and the sieve will probably notice quite a good improvement compared to it. Yeah, not as much as I hoped for, but still we see it runs faster than the new approach. And if you make n ever bigger, you'll see how the difference develops. There are more approaches of how we can calculate prime numbers. And as I said, there are whole books, and it's an active research topic of how to efficiently generate how to generate efficiently prime numbers. But we saw already with a little bit of work, we can already massively improve. And the sieve of the era Tothinus can actually be visualized quite well, while my LaTeX slides here cannot visualize. I will just open this in my browser briefly and we'll look at it together. So just give me a quick second to switch to my browser, and then we can watch it in the browser. This time we can record this easy because it comes from Wikipedia and we're refreshing. So what we see is we're starting with the 2, and the multiples of 2 get eliminated. So 2, 4, 6, or 2 stays the 4, the 6, and so forth. Then this goes on with the 3, but not 2 times 3, but 3 squared, which is 9, and then adds 3 on top, which is 12, 15, and so forth. So we see how this sieve very efficiently removes all the multiples of the prime numbers. So the prime numbers we have so far are 2, 3, and 5. 6 is eliminated, so 7 would come, and then it continues with 7 squared, which is 49, and then starts adding 7 on top, which are the yellow ones. So this is a very good animation of the sieve, and we see actually runs super efficiently, and it's much better than what we tried before with going through all of them, which was a very naive approach, crossing them out. Then the squared approach helped already to massively speed it up. And then we looked at our third approach, which was even better, and then the sieve. So we see with actually just like 30, 35 minutes of work, we already built quite an efficient algorithm, not as efficient as the current ones debated in research, because it's an active research field of how to generate these prime numbers efficiently, but it wasn't that difficult to actually build this. It can be shown, but this is not relevant to the course, what the complexity of our sieve is. The complexity of the sieve is, and this can be shown in books, for example, but how to show it is not relevant here today. The complexity of the sieve is O of n times the logarithm of the logarithm of n. So we take the logarithm of n, the logarithm of the logarithm, and we multiply that result with n, and then we have our O complexity. This sieve has, like the third approach, a space complexity of O of n, because I need this list of true and false entries, and I need to successively eliminate the true entries. So it comes with a higher space complexity than the approaches before, but leads to massive speedups in the running time. So I hope you got a little bit of an understanding of how to calculate or how to generate prime numbers. If you're curious to see more algorithms, check in Google Scholar for recent publications, or there, as I said, there are whole books on this kind of stuff. But no matter whether you're studying AI or cybersecurity, because that's the majority of the students taking this course, you will need prime numbers. If you're from cybersecurity, for example, for encryption, the AI students will also need them for other problems. And now I think you got a good sense of how we can generate prime numbers efficiently. With that, we're just at the end. These were the numbers that I measured when I ran this at home like a few years ago. I had created this chapter or sub-chapter here on prime numbers a few years ago because I always like preparing new slides for selected topics in that course, but I'm not able to teach all of this every year. So this is actually the first time I'm discussing this prime number section here in this course, but when I created the slides a few years ago on my old MacBook, which was from 2019, I think, when I bought the MacBook and I created these slides maybe 2 or 3 years ago, these were the numbers we saw. Now with my current computer, it took like 106 milliseconds instead of 350. The exact numbers don't matter, but we see the speed ups and the proportions are probably quite comparable to what we have seen. And we get a huge speed up just by doing the first trick that we did. Then the second trick leads to another speed up, and then the sieve leads again to a speed up in terms of the proportion, not as massive as the other speed ups, but still a further speed up.